Hi everyone, welcome to the most confusing video in the probability section. This one's all about Markov chains. The general gist is that we can use matrices to figure out what's going to happen in the future if we know some probabilities. So I think the best way to do this is through a bit of an example. Anyone who plays sports, you'll know a bit about teams that either fall into streaks or they fall into ruts. So if you're on a bit of a winning streak, you might feel pretty good about winning, and so you might be more likely to win the next game as well. Whereas if you're in a rut, if you've lost the last game and you keep losing, maybe you'll feel like you're going to keep losing in the future too, and so maybe you will. So let's suppose that there is some sort of sports team, and if they win their last game, so let's say if they win their last game, they're going to win the next one with a high probability. So let's say if they win, given that they won last game. Okay, so if they win, given that they won their last game. So let's write that as a probability of, let's make event A a win. Win, given that win game 2, given that they won game 1. And let's say that's pretty high, they're pretty good. They win again with 0.9 probability. Whereas they lose game 2, given that they lost, with pretty high probability as well. So probability that they don't win their second game, given that they didn't win their first game, that's pretty high as well. Not quite as high because they're a pretty good team. So let's say that's 0.5. Okay. So if they won their last game, they're probably going to win their next one. If they lost their last game, there's a 50-50 chance that they'll win or lose their second game with a 0.5. Okay, so we can also say then, we can figure some things out. So remember, A1 is their first game. So they'll either win it or they won't win their first game. And A2 is their second game. They'll either win it or they won't win it. So let's figure out some probabilities here. Using one of these. Okay, so here we've got the probability that they'll win their second, given that they won their first. And that's probability of 0.9. Here, this is the probability that they will win their second, given that they lost. They win, given that they lost. Here we've got the probability that they will lose their second, given that they won their first. That they won their first. So obviously, they can either win or lose. So if they win again with the 0.9, they will lose with the 0.1. Okay, here this is the probability that they will lose their second, given that they will lose, that they've lost the first already. And we've told that's a 0.5. So obviously that means they've also got a 0.5 chance of winning even when they lost. So there we go. We've created a bit of a probability table here to give us all possible situations of whether or not they'll lose or win their second game, depending on what happened on the first game. And we call that thing a transition matrix. So we'll use a big T for transition matrix. And let's write it down in matrix form. We've got a 0.9, 0.5, 0.1, 0.5. There we go. There's a transition matrix. And to find what's actually going to happen, so suppose we've got a question of what actually is going to happen in their second game, depending on what happened in their first game. So in other words, what's their state? Let's call it state. The book uses weird notation here, but let's call it state 2 for game 2 is equal to the transition matrix multiplied by state 1. And let's call state 1 like the probability that they're going to win their first game. Okay. So let's set this up in a bit of a matrix form. So let me write this in matrix form. We've got the probability that they win game 2, and the probability that they lose game 2 is equal to our transition matrix. This matrix here, 0.9, 0.5, 0.1, 0.5, multiplied by S1, the probability that they will win their first game, and the probability that they will lose their first game. There we go. So that will, if we do this, it will tell us, we just need to put in our values for the probability they win their first one or the probability they lose their first one, and that will tell us what the likelihood is about the next game. So let's suppose in this particular example that the probability that they will win their first game is 0.6, and which means the probability that they will lose their first game is 0.4. So this value here is a 0.6, and this one here, 0.4. Okay, so now we've got to do our matrix multiplication to find out the probability about their second game, whether or not they win it, or whether or not they don't win it. Okay. So to get the thing that goes in this top position here, that's the row 1, column 1 position. So we have to multiply our row 1 by our column 1. Remember our matrix multiplication, may need to go over that again. So it's 0.9 times 0.6, 0.9 times 0.6, plus 0.5 times 0.4. 0.5 times 0.4. And the next one is the row 2, column 1 position. So it's 0.1 times 0.6 plus 0.5 times 0.4. So now we just need to plug all this into a calculator or possibly even our brain. So 0.9 times 0.6, that's going to be 0.54, plus half of 0.4 is 0.2. 0.1 times 0.6 is 0.06 plus 0.2. So that is then 0.74 and 0.26. So there you go. You can see that these add to 1 because obviously they have to either win or lose their second game. So the probability that they win their second game, no matter what happens in their first game, probability they win their second game is 0.74. And the probability they lose their second game is 0.26. So yeah, there you go. That's how you can use transition matrices to figure out the next state. Now, suppose that we wanted to know what would happen in their next game. We would do the same thing again. We would use this same matrix, but so this equation here would progress along one step. So we'd now be doing their third game is equal to the transition matrix times what happened in their second game. So this S2 would be the matrix we have just calculated, this one here. Okay, another way of thinking about this S2, remember from up here, S2 is T times S1. So in other words, S3 is T times S1, which is, of course, just T squared times S1. So there's a bit of a shortcut. If you want to, you can just keep squaring the transition matrix if you're asked whether or not they're losing their third game or not. Okay, so that's basically how you do these questions. Okay, that's how you do them, but I haven't explained why this actually works. And before I do that, I think this is probably by far the most confusing thing that you're going to come across. So just to help you out, I'm going to say that I'm going to do one extra example. Before I explain why this is even allowed, where it comes from, before I explain that, I'm going to do another full example. And this one's going to be about the weather. Classic probability situation. So imagine... imagine that that we know that if it's sunny, it's more likely to be sunny again the next day, and if it's not sunny, it's going to be probably not sunny again. So let's call event A sunny. Okay, so and we'll say that the probability of it being sunny on day 1, given that on day 0, yesterday was day 0, is sunny, so no dash means sunny, with a probability of 0.8. So it's probably going to be sunny if it was sunny today, if it was sunny yesterday. And if it was not sunny, A0 dash. So A0 dash means it was not sunny yesterday. So if it was not sunny yesterday, it won't be sunny today with a high probability as well, 0.7 for that one. So let's figure out our transition matrix. Remember, it's the A0 dash, and A1 dash. Okay, so A1 given A0, that's a 0.8, which makes that 0.2. A0 dash and A1 dash, that's this one here, 0.7, which makes this a 0.3. So that's our transition matrix. So we can jot that down. Okay, there's our transition matrix. Now, suppose our question is this. Suppose yesterday was sunny with probability A0 equals 0.6. Okay, and that means that yesterday it wasn't sunny. A01. It wasn't sunny yesterday with probability of 0.4. And we want to know what is the probability that it won't be sunny on day 3. Okay, so day 0 is yesterday, so we're looking for day 3. So in other words, we're looking for probability A3 dash, because dash means not sunny, won't be sunny. That's what we're trying to find out. So here we need to think, and we need to go, okay, well, to get from state 1, so that's like our day 1, transition matrix times our day 0. Then to get to day 2, it's transition matrix squared. And to get to day 3, it's transition matrix cubed. Okay, there we go. So what we've got to do to find our probability, let's write this out. So this is probability of A3, probability of A3 dash. Here's our transition matrix, 0.8, 0.3, 0.2, 0.7, cubed, which we can do on the CAS, And our starting position is written here, 0.6 and 0.4. 0.6, 0.4. So this is definitely one to just do on the CAS calculator, because matrix cubed is going to be a bit of a pain in the backside. So once you do that on the CAS calculator, you select the correct result we're looking for, which will be this second one on the bottom. And that's it, you're home. That is the full answer. But this video is getting a little bit long already, and there's still plenty to go, so I won't cover that just yet. One last thing to say, however, is that if we were talking about a different situation, like instead of how likely it is that our days will be sunny, if instead we're talking about how many people out of 100 drink coffee or something like that, these numbers don't have to be probabilities. They could be numbers of people, or something like that. Maybe. Okay, whereas the transition matrix, whoops, these ones here, must be probabilities. They must be probabilities. So you're never going to get something in here that's not between 0 and 1. Okay, it has to be between 0 and 1 for it to be a probability. Whereas these ones, they could be possibly just numbers. Okay, so we've just done a bunch of examples about how to use these things, which, by the way, they're called Markov chains. Okay, it's a very important thing, Markov chains. Markov chains are what we're talking about here. We've done some examples using them, but we haven't at all discussed how they were even discovered. How did they put these matrices together and figure it all out? So I want to spend a little bit of time looking at that now. It's going to take a little while, so if you're happy just with the examples, you might want to stop here. But if you're a bit more brave, you might want to keep going and figure out how in the world do they figure these out. Okay. And here's basically how they did it. Okay, let's think to one of these examples where we have a tree diagram, and either event A could happen, so let's say yesterday's A, or A could not happen. And then we go again, possibly with different probabilities, so A1 could happen, or on day 1, A1 could not happen. And similar over here, on A1 could happen, or A1 could not happen. So this is kind of like our sunny day, and this is our not sunny day, and this is our sunny day on day 2, not sunny day on day 2, or not sunny day, or day 1 I should say, if 0 is yesterday. And these all have probabilities associated with it, so maybe it's a 0.7 and a 0.3, and then this one's the conditional one, so maybe that's a 0.8 and a 0.2, and maybe this is a 0.6 and a 0.4, something like that. Are sort of similar values to what we've been using. And then you can keep doing more and more days. So you keep doing more and more days if you want to, using our transition matrix. So let's think about some equations that we've got coming out of this. So suppose we're looking for the probability of it being sunny, probability of it being sunny on the first day, given what it was on yesterday. Okay, so we're looking, that is this one here, because this ends up with a sunniness, or it's also this one here, which ends up with a sunniness as well. So that's going to be this probability A0 multiplied by the probability here. This is the probability of A1 given that A0 happened. A1 given A0 plus, now this one here, that's the probability of A0 dash times the probability A1, A1 given A0 dash. Cool. Now let's look at the probability that's, say, not sunny or whatever you like there. Probability of A1 dash. Okay, so it's these other bits. So now it's this one here. So that's a probability of A0 times the probability of A1 dash given A0. And the second bit over here, probability of A0 dash times probability of A1 dash given A0 dash. There we go. So we've got these two big equations, and we can write these two equations in matrix form. So obviously here we've got our probability of A1 and probability of A1 dash. Now you're going to notice that we have, going into this bit here, we've got our probability of A0 occurs in both, and our probability of A0 dash occurring there and there, which means this is going to be an A0 and probability of A0 dash. Okay, so that when we multiply this one across, it's these two appear there and there. And we multiply these two across, that's this one being multiplied through here and here. So let's look first here and here, gets multiplied by that and then that. So the first one must be this, must be the probability of A1 dash A0. And then the bit that's next to here, this bit here, remembering our matrix multiplication hopefully, is this. And a similar thing here. So you can see this transition matrix is exactly what it was earlier, and you can show that by, like, obviously it's the A0 and then the A0 dash is there, and it's the A1 and the A1 dash going through here. So just as like, these are just sort of references to help you understand the table. Okay, so that's how it comes about, and that's how you're allowed to use these transition matrix things to form our Markov chains and find out what happens in the future. So that one's probably the most complicated one for this entire chapter. So I'm going to leave it there, but you may need to watch it again from the start after having a bit of a go yourself at some problems. So best of luck, and I'll see you in class.